Professor Anurag Misra presently serves as visiting professor in the Department of Civil Engineering at Indian Institute of Technology, Jammu. He obtained his master's from NIT Kurukshetra and doctorate from the Queen's University of Belfast in United Kingdom. Professor Misra has worked in both industry and academia at various capacities, including as Chief Executive Officer and Director of the university. His industrial expertise includes pre-engineered structures, steel concrete composite, precast elements, and prefabricated steel structures. In addition to this, his research interests extend to utilization of waste in concrete, durability of concrete repairs, and non-destructive testing. In his academic career, he has worked on several national and international research collaborations and over 200 consultancy projects. With this brief introduction, I would like to invite Professor Anurag Misra to initiate today's session.
Right. Thank you, Sanchit Gupta. If I'm correctly taking your
Yes, sir.
name.
Yes, sir.
Right. Thank you very much, and it is my pleasure to interact with you all in this session, which I was asked by Professor Sandeep Chaudhary that it has to be on precast and prefabricated construction. So, in fact, these two, although similar, but are quite different fields. So I thought of discussing one, but then still I have tried to combine both the streams in this discussion. Mostly, I will try getting the basics of this technology and then the field experiences attached with this these two main precast and prefabricated construction techniques. Although it is not new these days, it's gaining popularity to a good extent, I would say, and at a very fast pace. This whole topic, we would go with briefly types of pre-engineered buildings, material, very brief on design and detailing issues, some construction practices, the types of precast elements. We will move from one domain to the other. Then we will discuss some of the production and construction methodologies and some issues related with them, and then try concluding the topic. We will have some time also, maybe we'll leave some time for the discussion as well before we close this. So when we are talking about the prefabricated structures or pre-engineered structures, so why we are calling pre-engineered structure? Because normally in construction, we have a site and we start constructing from foundation to the columns and roof, etc. And in case of bridges, we go again foundation, pier, and then superstructure. But in pre-engineered structures, mainly we are manufacturing the components of the whole building at one location or factory. Location means that it may not be a factory, it could be a yard especially created for it, which could be, you can assume it as a factory. And then you take it to the site and do the assembly of these components. So what is important here, that you have to think of modular components, that the repeatability of the size and types of components has to be there. And then you have to adopt a mechanized process for production, and obviously then taking it to the erection process as well. So modular components means that all the components you are going to make, those columns, beams, etc., they have to be of the standardized definition, so that the production in an assembly line becomes easier. So that is what this means. So here the manufacturer is designing the structure as well. So the design office is attached to the manufacturing company, and they are manufacturing the building components, and that inventory which they are going to use, that they also define, because that is what is making it more interesting. This is one of the most important points, that how can you control inventory if you are going for a mechanized process of it. So what you are trying to do, that you are buying things in bulk and trying to minimize wastage. So whatever raw material you decide, um, you are ordering in bulk and then trying to minimize the wastage, and that is how this whole process results in a viable and economical, if I am allowed to say, economical solutions to the buildings and different other types of structures. Normally, when we are looking for the raw materials, are talking about the steel buildings. It is a common notion that steel buildings, or even for that matter steel bridges, are more expensive to construct, and that is why many times the agencies or government organizations sometimes retract back, because of the cost involved. The initial cost involved in the project is high. But if we control these days the way we are working in the industry, uh, to a very great extent, you can offset the cost, because these days time is also money. So if you are able to save time, you are offsetting those additional costs uh, spent on the difference, are different uses of the material. You are going for mainly a steel structure. So if it is going to, if you compare the cost wise, that column and beams cost, and frame construction of a frame cost, that is high. So you are minimizing that by uh, creating bulk orders, and also minimize the wastage in whole of the material you are using. um, so why we want to go, because there is a good control over design and fabrication, which results in lighter structures, um, because the modular design is there. So the designers are having experience in the similar kinds of design, and they are doing the experiments also in their factories. So a very good control over design and fabrication is available, and which is resulting in lighter structures. And that is also because when you are going for lighter structure, you are saving material, but not only making it lighter, the wastage is also minimized to a very great extent. And that is how you save time in materials. And then you are deploying a mechanized construction, and which is again saving lots of time. And the time is, as I said, money, and you are saving money on the total construction project's overall cost, and that makes the system viable. Right. I think my keyboard has stopped working. So once the fabrication is over, then you have to transport the components to the site, and the these components are erected there wherever you are looking for site construction. So because the whole of the work has already been completed, so it is very less labor intensive, uh, because most of the fabrication is complete, and shorter construction time we are able to achieve, and quite easy as far as construction is concerned. Then there are certain other advantages. Typical steel buildings would allow large displacements before collapse, and uh, that is actually giving a kind of mechanism which is working very well towards the energy dissipation and would be quite helpful in the structures like in the regions like earthquake regions. Now, what are the issues when you are going in pre-engineered buildings? So you have to protect against corrosion, because if you are going for prefab construction or prefab building, steel building, the corrosion is one of the problems, and you have to protect that against corrosion. How? Well, there are, I think we will be discussing a bit during our discussion. And the protection against fire, that is again a major issue when you are going with especially high-rise buildings. And these days, things are being developed to counter that. And the last one is the design of joints, which is otherwise not very seriously taken, if I say that, to handle the earthquake forces. Everything is fine in steel buildings, but the design of joints becomes very, very important when the buildings are subjected to horizontal forces or the earthquake forces. So these are some of the issues which are sometimes, I won't say they are problems, but these are the issues which need to be attended before you are planning such projects and have to be dealt with properly. Then I'll quickly go through some historical steel structures. They are, in my opinion, some of the older pre-engineered structures, and this is one of them, that very famous Eiffel Tower, which was made into thousands of small pieces. So these pieces were made, and then the erection was done for making this beautiful structure, which is still standing and is admired by the huge number of people from around the globe. So that is how the smaller components you make, so that you can easily transport them, and then you just go and assemble them in place where you could actually do that in a faster pace and more accurately. This is another structure which I personally like very much, but it's a very old railway bridge in United Kingdom, and you can see that how this structure is designed. This you can see here that huge pipes all are in pieces welded at site. So this is not falling into the category of pre-engineered buildings. But what I want to say here, that they are all made into components and then erected at site, maybe with the help of site welding as well, because in those days, maybe around 30, 40 years back, a big challenge. And it's a huge bridge, and you can see how beautifully some of the members are just like your space frames, because these members are not compression members, so you don't need thick components, and that is how the structure was designed and executed at site, taking these smaller components, assembling them together at site, and creating such masterpiece facing the sea and standing for more than a century. You can see that this is also being painted in red, the red oxide for corrosion protection, and this is a continuous process on this, because it takes huge time to complete the painting, and that is how it is being protected. So what are other types of these days what we are using as pre-engineered structures? These are some of the types of pre-engineered structure. You can see that some industrial shades, a very common one, where all the components, whether these are column, beams, all of them, is there a question, or may I request everyone to please keep their mics on mute? So industrial sheds where you have beams, columns, component fabricated and then erected at site. Then also you have some of the structures which are envisaged and created in components assembled uh, to to create a good aesthetic view, and some toll plazas, uh, also residential structures, and these are increasing in India also now these days. That lots of steel structures are coming up with different types of infill panels and deck casting, etc. These are some malls, shopping complexes where you could actually see that the columns and beam structure is going on, and you could do the casting by putting the deck sheet at different levels. So here the structure frame, um, the assembly could go on several stories, and the casting in different stories can carry on. It is not necessary that the casting of the slab of one story should be finished before you go to the next story. This is a hospital building where you can see this is all steel components and the deck slabs casted, and there is some open space as well, which is going to be filled with the precast stairs. So normally, when you are going for pre-engineered and precast structures, many times these two are combined together to get the benefit of both the technologies. So these are stairs, and in Europe or United States, these are very common things that people don't cast the stairs. They get precast ones and just assemble them there. This is a convention center which is made of completely steel, and it's a circular building in plan, and quite quite impressive. And the time of construction is also very fast. It's a huge circular convention center. This is one of the metro stations. This picture I have taken from metro station when it is under construction, and you can see a good help to the architects that whatever shape they are designing, the steel structures are able to provide innovative shape, not wasting too much time in construction, because as you can see that this whole thing is divided. This is one piece. If you are able to connect, this is one piece, this is the second one, this is third, and this is the fourth piece, right? So this whole portal is created into four components, and they are similar components. You program it, put it in your machine, and these built up sections are, let's say, this built up section you need 2000, so you can repeatedly create and make the structure. This is another one. You can see that this open structure, because this metro rail is passing over a flyover, so height was quite high, and you needed to cross this here. So some of it had to be cast in situ as well. The rest of the slab at the lower stories were all precast, and the this component, this opening, you can see that you have certain supports here, and the, the prefabricated components, the girders, were used here for construction of this metro station, which is lying just above the flyover. So you can see that these are the box girders. So two main box girders, and they are made in pieces which you can erect and assemble at site. You can see there are certain splicing joints are here. So these joints, after making them into piece in one piece, then you just erect them, and then these cross beams, etc., are done simultaneously later on. So this whole thing is planned in a way that, as I said, this is a metro station. So these cross beams, there are two main girders. They are box girders, steel box girders, prefabricated. And then there are some cross members which are joined at the bottom of this cross girder. It has been purposefully done because you need to have platform here and the rail has to run on this level, right? So this depth of the girder is decided in a way that the whole thing comes as required. The rail is here and your platform is here. So when the metro rail comes, you are at the level of the platform. And that is how this has been planned. So now the casting is going to happen for the railway line. So this is at a lower level, and whereas the platform lever is being attached towards the top of the girder. If this is the depth of the girder, so your platform is attached here, and the deck level is attached to the bottom of the you can see this deck level is where the rail would come, is attached to the bottom side, and the platform is cantilevering from the top of the girder, which would provide space for the passengers to board the train on this side. So that is very easily, and this was done very fast because all the components, when we designed, it was designed, made in components, and then fabricated there, brought to the site, and then the erection was done just for the casting. You can see here after this assembly, these are this assembly is being done. So the brackets were already provided. Now the cantilevers have come on top, and then we use sacrificial shuttering for this, and then reinforcement is put and the casting is done. So it's a very fast construction, and probably it would have been very difficult to do this construction without disrupting the traffic on the flyover. So that is how we can actually harness the advantages of the pre-engineered structures, are the advantages of dealing with the design and fabrication of structures. So you can see that the cantilever members are coming out. This is just before you start putting the longitudinal members as well. So the girder is there, the main girder, one and two main girders, and inside between these two girders, there are cross girders which are at the attached to the bottom of these box girders, and the platform cantilevers are coming from the top on both sides, right? So they would provide the space for platform. And you can see the traffic is continuing. Then you have large span structures where you want the, this is one of the warehouse building where you could see that this building is about 200-meter long and then 75-meter wide. So depending on the requirements, some intermediate spaces, the supports were created. And you can see that the structural components are made in pieces. There is one joint here, the another one is here. And depths also are varying because these are the points of contraflexures. And the same you can see here, that is the connection to the column. And the structure is now again categorized into 5-6 types of members, which are repeated in thousands. So the fabrication or the fabrication of the components becomes very easy, and then you can see there are few people who could actually create such huge spaces for storage. Just one by one, they are brought together. The bolting is done. Then you start putting the purlins, bracings, etc., and the structure is erected. Right. So now we just move on to, after going through the types of structures, we move on to some materials which we are especially using for these pre-engineered structures. Obvious is the structural steel we are using. Till now, we have been dealing with FY250 mild steel. And then nowadays, most of the pre-engineered companies have started using FY350, that is E350 steel, which is becoming reasonably popular because it saves money. Earlier, the problem was that E350 was not available very easily in the market, but because the demand has increased, so most of the steel companies have started producing in bulk as well. And uh, I won't say that it is completely done, but yes, if you want an order, you are able to get from all the good companies. So this is one material we are using in that. Not going to discuss much. And then we are going for light gauge steel sections. They are one of the very important components of the whole system we are creating, where we are having the thin sheets and molding them or the rolling them into different types of sections, and using them to our advantage at sites. So wherever we want to bolt certain kinds of purlins. So these days, most of the sites where purlins are being used, they are mostly light gauge steel section. They are roll formed. So you take a thin sheet and then whatever Z section or C section you want to create, rather than we preferring a channel section, these light gauge steel sections are being used, and they are responsible for giving huge economy to the such projects. Then we have corrugated sheets or profiled sheets. These days we are calling the conventional corrugated sheets. These are we are not many times using these days. Normally, such profiles are used um, in construction. Similar types of profiles are also used for decking system when you are doing the casting of the structure, slabs, etc. Because when you are, so they are eliminating completely the time of doing the shuttering. When you are using these deck sheets, many times they serve as the reinforcement as well, and you just do the pouring of concrete on top of them, no requirement of shuttering for casting the slab, and that saves huge time and obviously results in the economy of the structure. Then polycarbonate sheets we are using quite extensively, and aluminum composites. So these two are new ones. Many times we are using multi-layer polycarbonate sheet for giving insulation, and also the daylighting, utilization of daylighting, because when you are going for ECBC plus norms, many times you need the daylights as well and want to reduce the AC load if you are going to use. So some of the steel, I am not going with this structural steel. We procure them in the form of plates, and then built-up sections are created for pre-engineered structures using HR plates, where you could get steel plates from 6 to maybe 50 thickness. Most of the range is this. Majority of it is used from 8 to 25. Uh, but these light gauge steel sections, you can say that these are the purlins where you could see the C section. Normally, when we are going for light gauge sections, we create this lip to just reduce the effect of the torsional buckling, because open shaped thin sections are liable to the warping. So to avoid that, normally the lip is created. And if you see this shape which is visible here, right, if one wants to create it, manual means obviously it is not possible. So these days CNC machines are available, or even rolling machines are available, where straight your this sheet is going, and while coming out from that side, it gets into the form C-shape form or Z-shape form, depending on what kind of machine you are using. So using light gauge steel section is quite easy these days, because making them to your design requirement, because most of the good roll forming manufacturers are providing facility for changing these parameters. For example, the flange section, the depth. So if you are looking for, let's say, 125 depth, it is easy. You could switch it from 100 to 125 and create your section very easily. You can also see there are certain holes. There are the holes for boards, expansion, the spaces for expansion movement. So these are very well could be created in that. And usually this roll forming machine is attached with some kind of press which would create the desired holes, whether it is elliptical, circular, or whatever, and that too in what numbers and spacing. So they are not done manually. The sheet goes, the straight sheet goes, you get the desired holes, whatever you have fed in, and the perfect profile is coming out from the machine, which could be used for your advantage. So these are other types of corrugated sheet, as I mentioned just now, that these are the conventional corrugated sheet you see. Nowadays, there are different types of sheeting materials. Some of them are GI simply, and the other one are zinc and aluminum, galvalume, and also these days you could see that colored sheeting is also there. So some of the companies have patented their this coating technology, and these days it is becoming very popular across India. And most of the sheeting exercise are the projects where these colored sheets are preferred, because they are having longer life or almost similar life to your GI structures, and they are aesthetic, improving the aesthetics of the buildings as well. So becoming very popular, and they are mostly in different shapes. So different companies have their own designs, that how many groups they are going to come, they are going to put, and how much is the coverage they are going to provide. So depending on the load carrying capacity, they change this groove, the trapezoidal section, and that is all possible with these roll forming machines. And you could actually use them for the roof sheeting, the wall cladding, or even the sacrificial shuttering for casting the concrete structures. If this picture is clear, you could see some indentation marks here on that. So these are purposefully created so that when you are pouring the concrete on top of it, it provides this indentation provides larger area and would have a better bond, so that the sheet and the concrete could work as a composite. But many times where the loads are very heavy, you use these shuttering these sheets as shuttering plates and are sacrificial shuttering, and lay the reinforcement on top of that. So these days the use of these deck sheeting has increased in the construction of bridges also. Right now we are doing few where no shuttering for the deck casting. It's the steel deck is used, and then you place the reinforcement on top of that, and that serves as the sacrificial shuttering. So that is enhancing the speed of the construction substantially, not allowing, because if you are doing some bridge or flyover or elevated road inside the city, it is very difficult to block the traffic for longer periods. So this technology is helping us quite a lot in dealing with this situation, and the pace of construction becomes very fast. These are some of the polycarbonate sheets. These are available in the market. You can see for different shades, different colors, and these are cellular ones. So you can see here that this is double layered cellular sheet, which provides a good insulation from outside, and also gives you diffuse light. So depending on the aesthetics and the imaginations of the architects, you could use different colors, because quite a lot of flexibility is available now. And also that what is the size of the covering, the span where you want to leave. Normally the sheeting, when we were using, we are using 1.2 to 1.4 meter spacing of the purlins. The polycarbonate with this arrangement, making it double layer, you are able to match those spacings as well. Then we are going with the aluminum composites, where some uh, insulating material is inside, and then you have the aluminum sheet on both the sides. So this is sandwiched, and then you provide the coating which actually suits you. It is which is making it durable, and also you're improving your aesthetic appearance. So that is what the concept of this aluminum composite, where inside it you have the material, polyester type of material, which is insulating, and then you have the aluminum sheets, which is covering from both the sides. So it is making as one unit with the help of adhesives, and then the outer surface you can use different types of coatings for making it beautiful and also the durable. So their use is also increasing quite a lot. You can see this example. This is this facade is the aluminum composite one. Uh, so you can see that how their use is increasing. Glass facade, and nowadays you won't be. It is merging with the gray color, so that the concrete building and this can go side by side without creating an eyesore. And it looks from outside that it is something like made in concrete, but the composites use is increasing. Different types of shades and colors are now available and being used. So when we are going for the design and detailing issues in pre-engineered structures, the first thing first that we have to take the loading very carefully, the dead and live load, and for the industrial and storage sheds, we have to consider wind loads very properly. Then the modeling issues, that how are we modeling our structure, whether we are going with single portal kind of thing, or designing it as a space frame. Then we move on to the analysis and design, and then design of connections, which is one of the most important points in steel buildings. Now here, after saying this, we have to be very careful that if we are making very small components, then the number of connections are going to increase. So we have to make a judgment and keep the component size in a way that we are achieving economy in design of those components, and also we are reducing the number of connections, because both cost money. As you just saw in one of the pictures I showed you for the industrial shade, where the points of contraflexure, the depth was quite small. So that length is almost okay for transporting through trucks. So we could actually put and save lots of steel in cutting that member into profile, and that is how we can economize the structures. So design of connection is very important, because that's one part which is many times not handled properly, and several failure example you can find because of the failure in the connection. So have to be very cautious while designing steel buildings and designing the connections properly. Then proper detailing is must, so that the fabrication becomes quite straightforward. And when you are there at the site, there are not much issues. Otherwise, many times the bolts are not matching. Holes and bolts are not going through. So if holes are not matching from the two components, you get lots of issues. So detailing has to be very proper. So when we are talking about the loading, dead load, we all know that we are going to have part one, the live load for the type of occupancy of the building. We choose from part 2875 part 2, and then we move to the wind and seismic loads, especially here. So I just wanted to mention that once we have done these two calculation of these two loads, analyze these structures, calculate the forces on the joint, and the joint design has to be given a very important consideration while completing the task. The design of the structure is easy. People just model it in the STAD and then you get the designs. But design of the connection should be given equal weightage, or I would say more weightage, and has to be dealt very properly. So wind load, we can put equivalent to static load, especially when we are doing the shade kind of a structure. Gust factor should be taken, not only just K1, K2, K3, VB. Have to assess what is the terrain type. The topography factor many times is important and governing the design. So in short, I would like to mention that this local topographic factor, normally we take one, but in undulating ground, we should take this factor also into considerations. Similarly, the terrain should be evaluated properly. That how are we going to have the different types of buildings around the structure, and what would be the effect of those on the structure. So just conceptualization has to be done, and we take the basic wind speed from the wind map of India, and then we calculate our design speed, wind pressure, and then very important that these force coefficients should be evaluated properly. I am sure that you must be considering that internal pressure coefficient and external and the net one need to be taken into design, depending on what is the opening provided in these structures. So this part has to be taken very carefully, and then the net pressure which is going to be exerted either upward or downward has to be taken for the design of various components. Wind force we calculate from this net CP and PZ, that is the your coefficient, design wind pressure, and these are applied on the structure for the analysis purpose. Also, we have to consider certain other conditions, that if your structure is something like that, you calculate the wind pressure depending on the slope, etc. But if your structure is not in this shape, for example, if this is the case, if something is coming cantilever, right, and so the wind pressure drastically changes, because it's like a kind of railway platform kind of loading, and is creating quite substantial pressures as compared to the other kind of loading we are considering. So some of the examples, like if the buildings are having certain curvatures, so if you are considering this, your force coefficient drops drastically. But if there is something like this, the force coefficient is going to be substantially higher than what we are going to take. So I don't want to discuss this design completely here, but with these examples, what I'm trying to just give you a flavor of what are the areas we have to be very careful while taking the force coefficient, because ultimately your design is going to depend on that. So if you have a concave shaped component, there's lots of pressure is going to be created from that side, and designers have to actually envisage that and take into consideration while designing them. Then also we have to consider the temperature loads. Wherever we are not considering temperature loads, so there has to be the building has to be broken at certain intervals, and proper precautions have to be taken for the making of the joints, etc. So when we are designing it as a single portal, usually we don't bother about much on the steel, the temperature loads. But if you have a building which is continuously going for a long distance and you are not taking precautions for the movement of the or dissipation of the temperature loads, you could see cracking in the foundation bolts, maybe sometimes the pedestals, uh, also the buckling of the or warping of the members. Buckling is not right word. Warping of the members, etc. And they start creating functional issues. So what I mean that if you are going to design this, so if the joint is going to be created at, let's say, 40-meter length, then the temperature variations have to be considered, and additional stresses which are going to be created along with the load and without the loads have to be considered for proper uh, functionality of the buildings in service. So this is one of the typical examples with different kinds of components. You can see here that these are the main frames where you have a rafter, column, the different frames. So you provide them at certain intervals, and then you have the purlins going, then eave strut, and then you provide some girts on the columns also for support of the sheeting. So if you have some distance, some wall here near the bottom, and then you are going to have the sheet cladding here, then for these supports you have to design them, and then these are the stays for normally in the form of thin rods, which would actually keep the members and alignment same and would help the stiffening of the wall panels. Right? You could also see some cross members because when the horizontal loads are coming, so these frames, you have two options. Either you go for design of moment resistant frame, or you create some mechanism which is taking care of the horizontal forces being applied on these structures. So to handle them, you provide the bracings which are able to carry all the horizontal forces and safely pass on to the ground. So this is a typical example. You could see that some roof bracing, and on the sides also you provide bracing for giving the lateral stability to the building. The same is being done in the multi-story buildings as well. So providing cross bracing in a multi-story building becomes difficult. So either architects help in providing some dead zones where you use these cross bracings, or you go for the moment resisting frames, uh, providing proper connections at the beam junction column. Uh, so how are we going with the analysis and design? I mentioned sometimes back, showed you a picture in the field that how the frame is designed. Uh, if you see that, if you are designing a conventional steel building, you go with this, that the beam size maximum moment, let's say 600. So you choose ISMB 600, provide that ISMB 600 here, and the same happens to the column ISMB 500 or 600. Uh, so these two are provided, connections are made, and then you make the frame. Whereas when you are doing, because we are not using rolled steel sections in pre-engineered structures, we are using all plates. So you could actually design a tapering section. I showed you in the metro station, it was a kind of curved section, curved eye section, you can say. So these things are possible, that the cutting of the plate is done in a way, and then you cut the flanges separately. It goes to the machine, the welding is done, and the member is, the built up section is ready. Now, after doing the connection, you can see that you could actually reduce the thickness here in the beam as well as in the column. So the net steel reduction is is huge, I would say, and that results on the total loads on the foundation and also the consumption of steel in the members. So for industrial shades, sorry, if you are using huge number of frames, let's say 5,000 columns and 5,000 beams, so the total effect on the project cost is substantial. It comes in the thousands of tons for bigger structures. So that is how the use of these is increasing, even if earlier we used to think that steel structures are going to be expensive. Then there are certain more things, some cleat and how the connections are going to be made of the purlins and the rafters or maybe girts on the vertical columns. So these are some of the things you can see that we design a cleat beforehand. Either it is welded when it is coming from the factory, or there is a provision for fixing that also at site, obviously not through welding. In pre-engineered buildings, we avoid welding at site completely. So this has to be all the either the supports or the components are attached to the made components made in the factory, or they have to be bolted here. So like you can see that the column and beam. So you have here the connection plates and the bolting is done. Similarly, you could there are holes here which you can use for fixing the purlins on top of them. So no welding is allowed, only bolted connections. You can go with and provide the structures at a faster pace. Now here you can see some holes in the web also. So sometimes at the supports, your moment of inertia requirement is more. And as I said, you are using thin sheets for creating these Z sections. They are cold form sections. So what is done that there is some overlapping done. Maybe from this side Z section is coming and that side Z section is coming, and they are getting overlapped for this certain distance from here to here, so that the extra moment at the support, that hogging moment at the support is taken care by both the sections, and that is why you provide the holes here so that they could act as one unit, and both the members are now taking the loads together. So there is no need for providing them separate purlins. Now the purlins are going one another and helping us in designing and economizing the structures. One more important point, when you are designing these, if the structure is a long one, it is also a good idea that we leave elliptical holes on these purlins, so that the movement of these purlins, because of the temperature variation, is also taken care, and the additional loads which are going to be created because of the temperature, that gets dissipated. So many times we do that when we are going for a longer structure, and we are trying to avoid the expansion joint. So basically, what you are doing that you are creating a smaller expansion joints at regular intervals. But one has to ensure that while doing that proper movement has to be available, and the members have to be together. These are some wall cladding being created with the help of a cold form section. You can see that there is a thin channel section at the bottom, and then some channel sections are actually put on these. So this will provide a double layered wall, which could be filled with insulation here, and also could be used for services, because you have to carry lots of pipes. Some places only electrical ones. Otherwise, you have to take some plumbing pipes as well. So usually they are double layered. So it is not a very flimsy kind of very thin sheet. So either you from the inside you could use the cement boards, and outside maybe aluminum composites. and the space between these two could be used for carrying your services, because these days, or maybe in time to come, this is becoming one of the very, very important aspects in multi-story building, or for that matter, any building. Everyone is becoming conscious and demanding that you cannot put just wires along the walls for putting the panels, the sockets and switches and the light panels, etc. There are air conditioning ducts as well. So lots of things are being experimented and being used to the advantage of the engineers. Now you can see there is another structure which is coming up. There are certain bolts you can see projecting from top. I will show in some other slide also that when you are going to cast it, we need to have this sheet has to behave as a composite material with the concrete coming on top. So if it wants to behave as a composite, this should be perfectly embedded. The strain between the two has to be same, so that they are not getting a different movement at that. Otherwise, it won't behave as a composite. So many times these the shear stresses at that level would try creating a force which bond may not be sufficient, because sheeting is reasonably smooth. So that is why we create first indentation. If that is not enough, we provide these shear connectors. So these are projecting and going into the concrete slab, and then this whole system is becoming rigid, and then this behaves as a composite section. So light steel framing, as I already told. Now, when you are going for moment connections, so welded or bolted, then we have to create certain cleats here. Some stiffeners also might be required, so that the warping of the tearing of the plate is not happening, because these members may be quite thin plates also. So a typical section I'm showing here that you can have, and there could be certain members here also in the L shape, which could be connected to this bolt and this bolt, this plate, for taking all the moment which is coming onto the joint. So we can go for moment connection, we can go for the combination of the two, and also sometimes we use these kinds of joists where we just need a support kind of thing. So you can see there are some steel beams which are connected to the cross beams, and then depending on the requirement, you could create some open web sections, they are called, some truss kind of structures which are attached to the beam, and then you could put the deck sheeting and complete the casting of the slab, and put it to use for service. So these are some of the examples of the open web sections where you have different kinds of trusses, and so they are making the structure lighter, and also, but all the time these are they are obviously taking more time to fabricate, and all the time you may not like, from the aesthetic reasons as well, to use them in these structures. So you simply then go with the steel members. But wherever you used to, you have to use RCC and steel, this steel combination. Roofing is only steel. We many times prefer this. You could go for long span structures as well. These are all open truss examples, where you could use them for longer spans. Some of them, again, they are created in pieces. These are all stadium cases where you could actually go for these kinds of components, bring them together, and do the site welding. Here, some site welding or you can design a connection which is just bolted ones, and you can deal with the huge spans this way. The steel building, we come back to the construction of these steel buildings, where you could see that the story wise, you could actually, right now the erection is going on at that place. The moment this frame is completed, you can immediately start erecting the beams on the upper stories. So you have created the complete list of the components, members. All the members are marked, brought to the site, and with the help of cranes, they will be taken to position, and just bolting is done. So I think this, even the ground, the lower floor is not cast. Your next floor is getting ready, and immediately the construction starts here. So many times it happens that you are third or fourth story, and the first floor, the casting of the slab is going on. So that is, and the moment you go up, the finishing also starts. I was showing this building earlier also, where I mentioned that there are some things left which is going to be filled up by the precast stairs. You can see the top ones. These are all deck sheeting kind of thing. So these are insulated panel, because this is the top floor. So slanting one, because in Europe actually you don't provide the straight ones. So this was the hospital building done by us long back in maybe 95 or so. So these are all panels, and these are the stair cases, and this is the connection from a typical building where you need moment connection. You have to actually increase the lever arm and create some kind of uh, connection which is able to carry the same kind of load. You cannot use different kinds of bolts. So you have to adjust your joint wherever possible in a way that you are able to manage the forces coming into the bolt. In some of these specifications, the connection to the main column is prohibited, right? So you can see that how do we deal with that when this is a circular column. So making connection to a circular column uh, is not a very easy task. So you have to come up with an engineering solution. So a small beam is a bracket is fixed, which is welded in the factory, and the connection is provided maybe 300 mm away from the member. So if you are using circular section for whatever reason, if architect is saying, or for the economical purposes, you do that, and then the connection could be like that, and then you have the cross bracings for supporting your roofing system. So sometimes I have seen that in this specification, they would prohibit making bolted connection at the column level. So you just avoid that bolted connection there. You take it slightly away from the columns. This is what the precast stair. You can see that this has been placed. There is a steel bracket attached. This bracket is actually like that, which is embedded into the concrete, and then it is placed here so that the stitch concrete or finished concrete could be placed here for making it plain surface, and you would not know that this stair is either you can see these steps going up, whether this is a precast or cast in situ. Then you have certain members for actually keeping it on hold, avoid buckling for these thin sheet members. So these are the intricacies involved in it, which could be this support is taken from the main beam, so that because these members Z section or C sections, they are very thin. So for avoiding the lateral buckling, you just have the connections made here. And then, as I said, you can go for long platforms, storage buildings, and any other type of building. Then the comes insulation. When you are going for the pre-engineered structures, how are we? If we are going for only um, the steel buildings, then it won't be insulated. Even if you are providing uh, boards, it won't be insulated. So that's a typical example of having double walled construction, where you have a insulating layer inside uh, the two walls, and that gives you a good thermal insulation. You can see that properly kept on hold, and would actually would not feel that it is a steel building. They are embedded something like this also, that concrete blocks, they are encasing this steel column in case you don't like the I shape. And they are also protecting the steel building from fire, because then it gives you a good protection from all four sides. Either you go for steel aluminum composites, so their insulation is also providing a good thermal insulation, or you could go for the block kind of construction. This is another one. Then yes, this I wanted to actually discuss. Here you can see that these are steel buildings. Uh, then these deck sheeting is used for concreting. Concreting has been done from top side, and this steel building is actually shotcreted uh, with a cement-based composite, which is providing you enough cover for the fire protection. So this is becoming very popular wherever you are going to use false ceiling, because in a steel building mostly you are using false ceiling in the structures. So you could actually do the shotcreting. It is very fast, and you can see that the whole steel beam is hidden inside the cement-based composite, which is able to provide good fire insulation, and that drawback is now not there. Also, when we are designing steel buildings, you have to go for lateral bracings, or consider the lateral stability. Either you go for K type of bracing, or shear panels, or straight the moment connections, but these have to be considered for taking the horizontal loads. And this is a kind of example. Either you provide, normally designers do some kind of shear walls, or the lift wells are placed in a way that they are able to handle most of the horizontal forces which are coming onto the structures. But otherwise, the bracing is a very common practice in these steel multi-story buildings. Uh, so how are we going for the construction process timeline? Preparation of the structural drawing. And when I say structural drawing here, those GFC drawings are not good enough, because you have to calculate or draw the shop drawings. Detailed fabrication drawing, each component is drawn so that the every hole has to match wherever it is meeting the other one. So each piece has to be prepared. So quite a lot of time is going, and that is why it is very essential that it is done in factories, so that this process becomes a repeatable process, and the manpower deployed there, they know how to draw shop drawing from the structural drawing, because steel detailing is quite I would say strenuous and very important, because the tolerances are in just a couple of millimeters. So the shop drawings are prepared, and I just tell you that because of the bad detailing, there have been few failures. I won't take the names here, but because of that, there have already been some disasters because of not proper detailing, even if you are doing the structural designs properly. Then once you have done the fabrication drawing, you have to go for the approval of both structures and fabrication drawings, and then you start fabricating. it's also a good idea that these connections are at least once checked for mock assembly at the factory only. So if the space is not available, that's a different thing. But otherwise, many people do that. That at least few of the joints are tested before it is shipped to the site, and then the components are shipped to the site and then go for erection. Uh, then we have certain types of foundations, foundation connection, where you have the members or the bolts coming from the foundation, and then you have to place your columns and get the plumbs right, and finally get away with that. So this is one crude way of doing it, where you are entirely relying as a pin connection. Otherwise, the sequence of erection is first the columns, beams. Once these two, although plumb is checked at this level also, then the plumb is checked. Uh, Weld is normally not there, but some designers are still preferring some site welding. Although, if you ask me, I would say that this should be completely avoided. Tightening of bolts, and once the final tightening is done, then the plumb checking has to be done again for the building, and then the column grouting of the column braces, and then rest of the processes could be taken up. Here you can see that in one of these structures that it has been placed. This is column, and then when we are going this as a moment connection, the connections are different. Maybe I just draw here. Uh, if you have, this is the base plate, this is I section, and you have a moment connection. So this is your top of the column. Your base plate is usually, these are the bolts coming out, and we do provide leveling nuts here. So first leveling nuts are done, and then on those leveling nuts, your base plate is resting for this column. Once these are placed in position, this leveling is checked, then you do the bolting on top. Now this space is still empty, so this space is then filled with some grout, so that this whole assembly, now this is a grout kept here. Normally we go for self-flowing concrete or having only 2 to 6 aggregates. So this is again the repetition of it, what I said, the construction sequence. You can see that this is here, decking is going on, the first level is completed, and the second level is being erected right now. So in different levels, the work would go on. All mechanical fastening is used, and it is not that we cannot create complicated connections. People are, wherever required, do such connections where large number of members are coming. You have to be innovative what kind of plates and inserts you are leaving there for making these connections. This is a splicing connection where you have one eye, other eye, and then you have the splice plate, and then the connection is done. Web splicing is also done. Sometimes the splicing place is kept from inside as well. So basically, like we are doing in girder bridges, the splice connection needs to be. These are some of the examples I have taken picture of. From this is from the same hospital building that which I was doing in UK, and you can see some neat and clean connection, for some in the web, some in the flange. Then this picture I just showed you that we go for the shear connectors, and now this is again a roof deck, and here you are this dark color. This color is also a fireproof paint. So this is a newer, you can say, technology coming up these days, and I won't comment that it is proven, although people say it is proven, but it is definitely working as a fire resistant paint, which is very expensive right now. But I think as the use increases, it will be coming to some limits. These are some of the examples of the deck sheeting where you could directly use this as reinforcement also for smaller span, where you have indentations for providing better shear connections with the concrete, and you just lay concrete over it. You can see the indentations are there, so you just lay the concrete, or you place the reinforcement on top of that, and go for the shear connectors on all sides, this side, and you have to design the connections accordingly. Here, if more connections or shear connectors are required, you can see large number of it because these spans are slightly larger in this case. So straight away you could do that and get the casting done. Also, this type of cladding is being used for the fire resistant. So if you are going for such panels and you do that, and after outer side of this, either you put some sacrificial or the architectural feature on it, or do simply the painting, or put some aluminum composite if your budget allows. So this is also actually to deal with the fire protection thing. This I already showed you. Fireproofing mixture is actually sprayed. Although it looks ugly, it is not, cannot be finished and should not be finished. It is just shotcreted. Now, when you are deploying this methodology, normally a covering is done either by the masonry blocks or maybe the composite or the aluminum, the cement boards, etc. And then you do the painting. So this gets concealed, and your building is protected from the fire. These are again the examples of the coatings for fire protection. And in a steel building, as I said, mostly false ceiling is used. In fact, these days, false ceiling for even majority of the building is in the RCC buildings we use because of the services we are taking. Either we are taking exposed or concealing them under the fire. Then we also quickly look at the castellated beams where we have to economize. So if you are going for an I-beam with this plate like this, having certain moment carrying capacity, and if you cut it like this, and just this place goes here and this place goes here, so you get a hole like that. So you have to just check the shear connections, and you can increase the moment carrying capacity to a huge extent. And as you can see, because of the parking, a large span is needed to be created, and that is how the main beam is a solid one, and all the beams are castellated beams are covering the huge spans. And the advantage nowadays, these are being used in the residential and multi-story buildings as well, because it is easier to carry the services here, because now the service people actually are always skeptical how the services are going to go. If they are going here, then the false ceiling further comes down, and in that case, the building height need to be increased. So this is how we deal with the castellated beams, and with these we could create larger spans uh, in tubular trusses. Now, very quickly, I would scan through that how they are created. Now, when we are talking about the steel construction, it is the normal welding process or cutting process. Now, this is I have taken from one of the plants, which is so your steel plates. That's the maximum size normally which you can handle, 12 meter. So you do the nesting with the software, and whatever components are required, the CNC plasma cutting machine, you simply need to feed the drawing, and this is now creating these stiffeners. So if there are 10 stiffeners required, it will take 10 stiffeners, and then if 2 webs are required, it will just cut 2 webs. It will match it. Actually, the whole area it is going to use, and there won't be any wastage. Whatever connection plate, if there is some thickness is going to be left, that will be used for creating the cleats, etc. And ultimately, when this machine stops working, the whole plate will be consumed. Right. So that is the best way of economizing it, because you are reducing the wastage. So this plasma cutting machine, the each cut is taking very small amount of the material, and very neat cut that is not possible by any other means. And you don't have to do it, just start, feed the drawing, and all the components, it starts from here, it will move to this point, and all the components would be cut. And once the all the web flanges, stiffeners are cut, then they are brought to an assembly line where the sizes are to be already arranged here for whatever type of beam you are going to create. Now, this example I have taken, especially this flange is 850 and this flange is 450 only. So it is unsymmetrical beam, which usually in horizontal pull through welding is not possible. So these are the ways now people have created such mechanism that if you want that, that can be created. This machine itself aligns it, and some tack welding is done while it is moving. And once it moves, it is something like this, moving on these rollers you can see here, and then it comes to the welding arm. So these two people are total, three people are required. They are not doing anything there. They are just removing the scale which is coming out after the welding. Right. So this is the robotic arm. There is one inside. So welding is going on both the sides of the eye girder simultaneously, and this beam is moving in a way that the continuous welding is achieved on this web and flange. So that is how it is making it advantageous and faster. You can see that this is actually coming out from the welding platform, where it has welded on one side. Once it is done, EOT actually flips it 360-degree, and in some of the plant, even that operation is automatic. So once the complete, it flips it, goes to the again in the same operation, and both side welding is done. So there is no manual welding done these days. This is a kind of a bird's eye view of the plant. It starts from that side where plasma cutting machine is there. Cutting is done, and then these plates, different components are stacked. Then you take it there, and the one machine, maybe in 15 to 20 minutes time, your 10-meter girder, because if you are going for, let's say, 30-meter girder, you have to make in three pieces. Otherwise, the transportation won't be possible. So that is how we control, and it actually goes through it. So in 15 minutes, 15 to 20 minutes, maybe one 10-meter girder is ready. 10-meter piece. So for creating one girder, you need three girders. With 30-meter girder, mean you need to create in three pieces. So 1.5 hours, and if one bridge has got four girders of 10-meter, 30-meter, so maybe in one day you can create one span. So that is the kind of speed we can achieve. And this is a steel building. I show sometimes. This is again a steel building. It is a completely steel building and has used, there is no masonry also. It is all the composite wall panels. Right. So this was the experiment done at IIT Jammu. We are not right now continuing with this straight away, because there are certain issues in the durability of the wall panels, and also again taking these services. But obviously these improved versions of these would be possible. So this is quite faster way of doing it. So this is how I wanted to present the pre pre-engineered structures. Now, uh, quickly go through. I have now, I think 15-20 minutes I can take more. Sanchit, would it be okay if I take
Yes, sir.
more?
Yes, sir. So the schedule is till 6.
Okay,
Sir,
okay, that's fine
you
then.
can extend also. Yes, sir.
Okay, okay. So precast concrete, again, that why do we want to go to precast concrete? I think these two go similar because you are aware that if the site welding is bad, in fact, the site concreting is further, maybe multiple times worse than that. So in precast concrete, we have much better quality control. It makes things faster, and again I say that it makes economical also, because when we are talking about the economy of the either precast or pre-engineered structures, and sometimes that's the only solution. You cannot afford to put the cast in situ girders here. So because this you can see that this metro line is going on the center of the road, and the traffic, you cannot stop in this area. So the thought of putting these kinds of portal for casting the pier caps, and then these brackets are left, which would be used for placing the girders. So from here to this, so you just bring the precast girder, put it, and traffic is not stopping. And then you can put precast panels for doing the slab, and then you can do the concreting on top. So how this precast concrete becomes economical? Very simple terms. If you are going to make, let's say, one 5-story block using precast concrete at some location, it is not going to be economical, because the whole uh, the planning and execution mechanism is expensive. But if you are going to do 5,000, might be it is surely going to be economical, and that is why good companies are now coming up with this technology, and quite extensively this has started and has to go further as we move on. In maybe 5 to 10 years time, majority or good number of buildings would be either pre engineered or precast concrete. So in precast concrete, would actually there are two types of things we are using these days in the field. One is die cast, which is normally used for making some precast elements. We'll just quickly go through them. And wet cast is being used for casting the elements, as well as bigger elements as well. So we how do we do that? Uh, this is a typical layout of the dry cast plant. So these days, very sophisticated machines are available for creating the precast elements. You can see here that there are some silos here. There are two different silos, and then two different mixers also. So actually, these are two concrete mixers, and in this dry cast technology, the concrete is completely dry. You cannot make a ball out of that. Otherwise, the components will not be made. So the whole hypothesis is that it has to be completely dry. Even the ball is not. You cannot make a ball, uh, or even normal vibrator won't be able to cast anything out of that concrete. So you are mixing the material, and usually it is all automatic plants. The material comes automatically to the mixer. The cement is fed through the silos, and here this concrete mixer is creating or mixing, taking water, whatever is required, and then you are seeing this conveyor. Because the concrete is very dry, like your a mixture of aggregate, sand, etc., and some water obviously in it, so it can very easily go through the conveyors. Now, once it crosses conveyor, it comes to the a hooper kind of arrangement, where this gets collected, and now here your machine is there. So this can cast different kinds of element. They can be masonry block, paver blocks, even the channel sections, RE wall panels, RE wall blocks, etc. The variety of things you have to think and design a mold for it, which could be very easily made and fitted in this machine. Now, this machine is equipped with a kind of vibratory mechanism, and also a very heavy compression. So both the things are applied, and that is why this almost dry concrete is able to get compacted, and you get an element. Now, keeping this dry means very little amount of water. That means very low water cement ratio is there, which is used for creating higher strengths. So once this casting is done, it is normally done casting on the pallets of steel, and then this automatically moves to this stacking mechanism, where it comes and all of them, it gets, there is a chain mechanism. So one pallet and then second, it moves up. When it is completely filled, this finger car goes here, takes them and keeps it in the curing chamber. And after placing this here, some of them which are ready, this takes them back, one is stacked back and leaves it here in this dispensing chamber. And from there, it goes to the cuber. So it is, these blocks are made in the form of cubes, and then forklift can take out, and it is ready for transportation. So here there are two, three peculiar things, that this whole operation is, again, there is no one involved in it. The water is controlled by the microprocessor. Uh, just two, three people have to watch and guard the whole thing. And then this casting is done. It comes here. It is now, this curing chamber is not using water. It is using the same water which has been used in the concrete, because this is all sealed chamber, and within that it creates humidity, and that humidity is maintained here. And once it goes out, and you have to achieve maybe, let's say, M30 grade of concrete. So many times we design in a way that this strength is achieved in 24 hours. So the production time is very fast, and you could create for bigger infrastructure. Otherwise, if you are looking for 10 lakhs blocks, let's say, and one small unit is usually able to produce 5,000. So even if they have enough space and can create continuous operation, but still 5,000, and if you have to create 10 lakh blocks, you can imagine how much time it is going to take for producing those blocks. So here this becomes very fast. These are the curing chambers, which is completely closed. Finger car comes, puts them, takes the ready one and leaves them outside. This is a picture which is showing the operation. This is machine, conveyor is dispensing. It goes on that side and comes from this side. So there are different types of sensors put when the material is going into the mixer. From there, the whole operation is completed. And what we can produce from there, these are some, that's how the uh, cuber, when it is coming on the conveyor, the cuber actually, this arm actually takes it, places it on one another. And if you are looking for, let's say, 12 layers, it stops after 12 layer, move, and now you can just do the binding. So maybe two laborers are put just for the binding with the machine. You can see that the strips are there. So the strip binding is done like you must have seen at many places at a airport, uh, and other places as well. So that is how this is a green product. No curing is required from outside water. Curing is done, and the whole operation is made very quicker. So I already told that no external intervention is required, and these are the components we are able to produce from these. And you can take the strength up to M80. 50, 60 is quite okay, but you can achieve up to that. The only thing is that your machine should be capable of creating that pressure as well as vibration. Being that dry concrete, it uses the very heavy hydraulic force for compression as well as vibration. So both the operations are used simultaneously with a very low water cement ratio, which is resulting in very high strength in these components. So these are some of the ori wall sections. So rather than we using these wall sections, these days these are becoming popular and quite effective as well. This is insulated masonry block, so it is completely avoiding the requirement of the double wall and saving quite a lot of area, construction area, because otherwise you lose about 20% area in the total area in the double wall construction. So these are some ordinary masonry block, and here you can actually get these polystyrene blocks. It goes into the mold, and the concrete comes here, and then it compression and vibration vibratory motion actually creates this block. You could go for hollow blocks of different keying mechanism, the insulated block, uh, the paver blocks, different kinds of them, colored curb stones. These days on highways, huge requirement is there, which normally the normal way you cannot achieve. And cast in situ has limitation because the ultimate strength there achieved with the technology is only 15-20. And if you do that, the deterioration of that concrete at roads, etc., goes very fast. Whereas these could be M30-40, which could be used for longer periods. These are some of the different shapes, different sizes, thicknesses for pedestrian and for the national highways could be done. Some decorative ones could also be produced. You have to create a mold for that. So these are some of the molds people are using, where you want the grass also put for this. And this is very effective on stabilizing the slopes as well. Normally, earlier, if you remember, pitching used to be one of the methodology for using this. Now, this beautiful landscaping could be done on slopes with these precast blocks. Then channel sections also. So you create, and within the city also, you have to just dig and pour the PCC and then put these blocks side by side, and you are done with large area in a day or even night. In the morning, people come, you have drained ready. Some slab unit or flooring units also, where you want to create a bigger floor in less time, no jointing, no concreting, you just bring the blocks and arrange them like that, tiling. Uh, Sorry, I think I had this picture. Then we go to the wet cast plant. So this is something I'm showing you, which is completely precast concrete. In this, even the columns are precast, nothing is cast in situ. All the beams, even these truss-shaped rafters, they are precast. So they are created in the factory, brought to the site. There are mechanisms how you can put these are placed in position with proper keying mechanism, and your erection is complete in no time as compared to the cast in situ. So this is exactly replicating the factory building, which could have been made in steel. Now this is in precast. I haven't seen this type of thing, although now precast flats are there. But in factory building, I haven't seen myself in India. This picture I took somewhere outside, and I think it was Turkey. They are using. I saw there are several precast buildings like that, which are completely concrete. These are some of the precast flat residential unit, which is very popular in becoming popular in India. Obviously, at several places, it's quite a standard technology. I'm aware there are many such blocks coming up in Bangalore and some in near Delhi also. Then precast concrete shell unit. Maybe you could use them as roofing, as well as if you want channels alongside, you can use them. So the shell folded plates, they can be produced in precast ways. Pipes, poles, sleepers, stairs. As I said, variety of things could be done in precast plants. Now, when you are going for a precast concrete residential units, even the wall panels are precast, and don't think that it is taking huge time. They're bigger pallets, maybe 4 meter by 8 meter kind of thing, and the outer lines are drawn with the help of the robotic arm. The molds are magnetic; they are placed. So in no time, just you have to place. The mold is fixed. Reinforcing cages, they are usually prepared separately. In the whole cage is prepared, and they are usually welded meshes. Just keep it, do the concreting. So one panel is ready. Once the concreting is over, next day take it to the curing chamber, and maybe depending on what strength you are looking for, maybe 36 to maybe a week, you are done with that. Beams, the same way. You could create beams, and wherever you want beam slab connection, you leave the stirrups on the top without casting. So pre-casting is done, and then the stitch concrete can be very little amount can be done on site. So that is how the connections are made in the at site. Uh, these are some of the precast culverts. So some U shape, you can put the top ones, and some of them are created in two pieces. One U shape is being used on the other U shape. So these are becoming popular. If you have to do the construction very fast, you have to simply do whole of the operation other than away from the site, bring it and just finish it off. So the design concept is same what we discussed. So I'm not going to discuss right now that you have to break up in smaller pieces. You have to go for the repetitive items and avoid connections, because in concrete connections are more difficult as compared to what we were talking there. So you have to simplify the connections. I'll give you one or two examples quickly that how can we do that. Safety of the individual structure and the structure as a whole, and obviously keep in mind that how you are going to transport thing and handle at site. Must have heard about the crane failures sometimes back. So these things should not happen, because when you go for very big members, then not only structure, there are other things also involved. There is crane failure, maybe the maneuvering is also important, and site which creates problem. So the plant precasting, I'm talking about now wet cast. So the process I already said, the molds, you can do pallets are different molds. Reinforcing, normally it is done separately. Casting is done, then the steam curing and transport. Normally steam curing is deployed. So such stirrups, uh, if it is a component which is repetitive, you stack them, and if it's a beam, you have to provide the stirrups are put in a way, even if they are more required, but they make things very fast. And then you have molds, just do the casting and take it to the other side. So this project I was involved in. I was telling you that once these are done, then you have to bring the precast beams. And what we did for, because if we would have provided the restrainers, would have created problem. So we left insert plates here, and after the beams are placed and the casting is done, we did the restrainers were provided in steel. So insert plate was there, and the brackets were created here later on to stop it in case of earthquake and so on. Now you can see here that then after placing the beams, you put the precast slab units, which are designed exactly the same way in all these stretch. The slab size was same, beam spacing was same. So same slabs were coming, and these are already resting on it. There are some holes which would be used for tying the reinforcement and doing the stitch concrete. So this whole operation is completed. You can see it is clearly showing here. So this is coming, and then that is placed here. So once these are placed, then you can do a finished concrete of very small thickness, so that the whole floor becomes one unit. Then you can also do the for infrastructure project. All these elements are made in 3-meter length, which is becoming very popular these days. Now this is something different. This was a 4-lane flyover, which needed to. So there was one way that we go for a 4-lane element, which is also very common these days. But here it is double decker, right? So there is one here, and on top of that, metro is also there. So both the things with that was not possible. So we designed a spine here, and this spine is placed and erected first, and then these triangular elements, these are also precast. They brought them here, and then you pull through the take the pre-stressing cables from here to the other side, and both the triangular elements along with this spine element, they are pre-stressed and they become one unit. So you can see it is this operation is done here. It is going on here, and this is still remaining. Some of the site precasting thing, not a good idea. That is why maybe for if we compare these types of blocks, maybe we go for the precast blocks or the factory made panels. Either we can go. The site precasting in the casting yards, where you can see, although they are taking good precautions for curing, the jute sack is here, and try to attach it to every part of the surface. But you can imagine that how effective curing will be able they will be able to do. Even if they are taking good precautions, uniform and very effective curing is not going to be possible that way. Either we go for a sprinkler system, it's a very good way, but that would involve lots of investment and wastage of water as well. These are some elements cast. Right. So that is how I would conclude that the pre-engineered structures are precast concrete elements. The main thing is that reduce time, they reduce labor, and because of the material time saving, they are able to produce economical and better quality structures. So that is what I would say. Thank you very much, and I think I have not taken more time. Maybe some other time I would like to talk more on precast because I hurriedly went through very small component of it. Thank you very much. If there are any questions, I'll be happy to interact with you.